In machine learning and AI, models do not learn from data in a purely neutral way. They rely on assumptions and biases that guide the learning process. These assumptions, known as inductive biases, help models generalize from limited training data. However, inductive bias can also introduce ethical concerns, such as reinforcing stereotypes, amplifying discriminations, or producing unfair outcomes. Here we will discuss what inductive bias is and why it matters in machine learning, and also examples of inductive bias in machine learning algorithms and AI algorithms, the ethical challenges and potential solutions. So inductive bias refers to the building assumptions that machine learning algorithms use to make predictions when dealing with new and unseen data. Without inductive bias, a model wouldn't be able to generalize. It would just memorize data without understanding patterns. And inductive bias is not inherently bad, but it can create ethical concerns when it interacts with biased datasets or societal inequalities. Since inductive bias is unavoidable, we must actively manage its ethical impact. First, we want to ensure datasets reflect real-world diversity, and that can reduce unfair inductive biases. And we also need to regularly test AI systems for bias that will ensure that models do not amplify discriminations. And AI should not operate in black box. Models must be interpretable and accountable. Governments and organizations should enforce AI fairness laws to prevent discrimination. So all machine learning and AI algorithms have inductive biases. They must make assumptions to learn from finite data and generalize to unseen examples. Without inductive bias, models would be unable to prioritize one hypothesis over another, making learning computationally infeasible. So we'll look at why inductive bias is necessary for generalization and how different machine learning models incorporate biases and the role of inductive bias in domain adaptation. So first, let's look at why do machine learning models need inductive bias. Machine learning models train on finite data, but must predict outcome for unseen examples. Inductive bias guide learning, making assumptions that allows model to generalize rather than just memorize data. Without inductive bias, models would be unable to infer patterns beyond their training data. In any given machine learning problem, there are infinitely many possible hypotheses that could fit the data. Inductive bias help narrow down this hypothesis space to make learning computationally feasible. For example, a model predicting house prices could assume higher square footages equals to higher price, rather than considering every possible relationship between features. Without bias, all hypotheses must be equally likely, making learning impossible. And there's also a no free lunch theorem in machine learning. This theorem states that without prior knowledge or bias, all learning algorithms perform equally well across all problems. Inductive bias is what allows some algorithms to be more to be better suited to specific problems. Learning is impossible without making assumptions. Bias is necessary for effective AI. So how different machine learning and AI models use inductive bias? Each algorithm comes with its own assumptions that shape how it learns. Choosing the right models means choosing the right inductive bias for the problem. For linear regression, inductive bias it assumes a linear relationship between input and output. For decision tree, it assumes that data can be split into hierarchical categories. For neural network assumes that features have hierarchical representations. There's also bias and variance trade-off. Bias is the assumptions a model makes to simplify learning. Variance is the model's flexibility to fit the training data. A high bias model, such as linear regression, may underfit, while a low bias model like deep neural networks may overfit. So inductive bias need to strike a balance. Too little bias leads to overfitting, while too much leads to underfitting. So we can use bias to improve learning with limited data. In specialized field, data is often scarce, such as medical imaging. Inductive bias allows AI to incorporate domain knowledge, making models more sample efficient. In healthcare AI, for example, prior knowledge that certain symptoms indicate disease helps the model learn effectively, even with few training examples. Inductive bias is especially useful when labeled data is limited or expensive to obtain. So inductive bias is essential for generalization, allowing AI to make predictions beyond its training data. Without bias, machine learning would be computationally impossible, as models would have to consider infinite possibilities. And different algorithms have different inductive biases, making them better suited for specific types of problems. The bias variance trade-off highlights the importance of balancing assumptions and flexibility in models. Inductive bias helps AI learn efficiently in fields where data is scarce, such as healthcare and scientific research. Machine learning models do not learn in a neutral way. They have built-in preferences that guide their learning. These preferences, known as inductive biases, shape how models generalize from finite training data to unseen examples. Inductive bias is not an error or flaw. It's necessary for AI to function. So, as we discussed earlier, inductive bias refers to the building assumptions that guide a machine learning model's learning process. These biases help model make predictions even when data is incomplete or ambiguous. Its inductive biases are necessary because they guide generalization, shapes the learning process, and balance bias and flexibility. So the wrong inductive bias can lead to poor generalization if it doesn't align with real-world patterns. So inductive bias can guide generalization. A model trained on limited data must still make correct predictions on new examples. And inductive bias act as the rules that shape these predictions. A spam detection model, for example, assumes certain words like free, lottery indicate spam, even if it hasn't seen all possible spam emails. Without inductive bias, a model can infer beyond its training data, and it influence on the training process because inductive biases prioritize certain solutions over others. They narrow down the hypothesis space, making learning faster and more efficient. So a linear regression model assumes a straight line relationship between input and output, ignoring more complex possibilities. This speed up training, but may limit the model if the real world relationship is non-linear. And inductive bias can balance bias and flexibility. A strong inductive bias makes a model rigid but efficient, so that's risk of underfitting. A weak inductive bias make the model too flexible, so that's risk of overfitting. Choose the right bias is key to successful AI models. So examples of common inductive biases in AI include simplicity bias, like Occam's razor, spatial locality bias, temporal continuity bias, linear separability bias, and so on. So let's look at each one of these example. For simplicity bias, also known as Occam's razor, it prefers simple models over complex ones when both fit the data equally well. So it helps prevent overfitting by avoiding unnecessary complexity. Decision tree, for example, use pruning to remove overly complex branches and improve generalization. Spatial locality bias, such as convolutional neural network in image processing, assumes nearby pixels in an image are related. So it enables convolutional neural networks to recognize shapes and textures, such as a facial recognition AI may assume that eyes, nose, and mouth should be close together in an image. Temporal continuity bias, such as recurrent neural network for time series, assumes recent events influence future events more than older ones. So this is used in recurrent neural network and transformers for predicting sequential data, such as stock price prediction models rely more on recent fluctuations than on year-old data. And linear separability bias, such as support vector machines and leading models, assumes the data can be separated by a straight line or plane. It works well for simple problems, but struggles with complex and nonlinear data. So support vector machine work well for text classification, but may fail on highly entangled data. Choosing the right inductive bias matters because the best bias depends on the problem. Choosing a bias that aligns with the data leads to better performance and efficiency. If the bias doesn't match the real-world patterns, the model may fail. For example, image recognition might work best if we apply convolutional neural network because it uses spatial locality bias. For speech recognition, recurrent neural network and transformers may work the best because they use temporal continuity biases. And simple classification problems, linear support vector machine might work best because it assumes linear separability. So understanding inductive bias helps in selecting the right model for any task. So we need to be clear that inductive bias is not an error. It's essential for AI to work efficiently. However, the wrong bias can limit performance or lead to unfair decisions. So inductive biases guide learning and generalization in machine learning models. Without bias, AI can't infer patterns or make predictions beyond training data. Different machine learning models embed different biases. Choosing the right one is crucial. AI ethics requires careful bias selection to prevent unfair outcomes. The bias variance trade-off is a core principle in machine learning that explains why some models fail to capture patterns that is overfitting, while others memorize noise that's overfitting. So high bias means model is too simple, missing important patterns, i.e. underfitting. High variance means model is too complex, capturing noise as if it were a pattern that is overfitting. The goal is to find the optimal balance where the model generalizes well to unseen data. So here we're going to explore what bias and variance mean in machine learning and how to visualize and manage the trade-off and then practice practical strategies to balance bias and variance. So bias is the error due to overly simplistic assumptions in a model. High bias models ignore complex relationships in data, leading to underfitting. So a model with high bias is too simplistic to learn meaningful insights. And variance is the error caused by a model being too sensitive to training data. High variance models learn every detail, including noise, leading to overfitting. For example, a deep neural network with too many layers memorizes training data but fails on new data. A model with high variance is too complex and does not generalize well. So why do we need a trade-off? Because reducing bias that is making the model more complex increase variance, so that's the risk of overfitting. And reducing variance that is simplifying the model increases bias, that's risk of underfitting. The goal here is to minimize total error, balancing both bias and variance. Next, let's explore different strategies to balance bias and variance. First one is cross-validation. So we split data into multiple training and testing sets to assess performance across different data samples. It helps detect overfitting early and ensures models generalize well. So cross-validation prevents variance from misleading us into choosing an overfit model. Second, regularization, such as L1 or L2 penalties, which I'm not going into details here. So this technique will add penalties to large coefficients to prevent excessive complexity. It reduces variance by forcing the model to focus on simpler patterns. So here we have ridge regression that use L2 regularization. It prevents overfitting in linear models. And dropout in deep learning helps avoid over-reliance on specific neurons. Okay, dropout in deep learning helps avoid over-reliance on specific neurons. Regularization can help keep model from memorizing noise. Ensemble methods such as bagging and boosting combine multiple models to reduce variance without increasing bias. It creates a balanced model that generalizes well. Examples include random forest that reduce variance by averaging multiple decision trees, and gradient boosting improves weak models iteratively while controlling complexity. So ensemble methods are powerful techniques to manage the bias variance trade-off. Next, let's look at inductive biases for different machine learning algorithms, starting with supervised learning. So let's start with more simple algorithm like linear regression. It assumes a linear relationship between features and then the target variable. It works well for linearly separable data, but performs poorly on nonlinear relationships. And decision trees prefers hierarchical, rule-based segmentation of the feature space. It can capture complex feature interactions, but it can overfit without pruning. Support vector machines seek to maximize margin between classes and assume clear separation. So it works well with high dimensional data, but it struggles when classes overlap. And k-nearest neighbors methods assumes instance close in feature space share the same label. So it's simple, intuitive, and interpretable, but the performance degrades in high dimensional spaces. Naive Bayes assumes conditional independence among features given the class. So it's fast and efficient for text classification, but it's less accurate if features are highly dependent. So each algorithm is suited for different type of problems based on its inductive biases. And neural networks, which we are going to elaborate later on, assumes complex hierarchical representation can be learned. So it's highly flexible and powerful for deep learning, but it requires large data sets and computation. So let's look at some good use cases for each algorithm and why. So for linear regression, a good use case is predicting house prices because we can assume a linear relationship between features such as size, location, and price. For naive Bayes, it can be used to classify spam emails because it works well for text classification with independent word assumptions. Detecting fraud in credit card transactions can be a good use case for decision tree or random forest because they capture complex feature interactions between transactions patterns. Facial recognition can be a good use case for neural networks such as convolutional network because they use hierarchical feature learning for images. Medical diagnosis using patient symptoms can be a good use case for k-nearest neighbor methods because it assumes similar patient have similar diagnosis. And sorting customer reviews into positive and negative categories is good for support vector machines because it performs well with higher dimensional text data. So understanding inductive bias helps us select the right models for the problem. So right bias help with better generalization, and wrong bias leads to poor performance. The challenge of model selection based on selective bias includes what if data is noisy. So high bias model like linear regression may work better. What if data set is small? High bias model require less data to generalize. And what if features interact in complex ways? So low bias models such as neural network decision trees may be better. So bias is neither good or bad. It depends on the problem. So all machine learning models have inductive biases that affect how they learn and generalize. Different algorithms work best for different problems based on their bias. Understanding inductive bias helps in model selection and improving performance. Unlike supervised learning, where a model learns from labeled data, unsupervised learning algorithms find hidden patterns in unlabeled data. However, these models still need inductive biases, assumptions that guide how they identify clusters, relationships, and lower dimensional representations. So let's look at how different unsupervised learning algorithms embed inductive biases and how these biases impact performance. Inductive bias for k-means clustering is the assumption that data points within a cluster are closer to their cluster center than to others. So it works well for spherical, equally sized clusters, but it fails on irregular shaped or overlapping clusters. Hierarchical clustering assumes data has a nested hierarchical structure where points belong to nested groups, so it can capture multi-level structures in data. But it's sensitive to noise. Outliers can distort hierarchy. Principal component analysis, PCA, assumes data variability can be captured in a lower dimensional linear subspace. So it's useful for dimensionality reduction, but it fails to capture nonlinear relationship. Association rule mining assumes data contains frequently item sets with strong association between items. So it can identify meaningful relationships in transactional data, but it can generate too many rules requiring filtering. And Gaussian mixture models, GMMs, assumes data is generated from multiple Gaussian distributions. So it's more flexible than k-means for irregularly shaped clusters, but it's computationally expensive and may get stuck in local optima. And autoencoders assumes data can be efficiently encoded into a lower dimensional space and reconstructed, so it can learn complex representations that are useful for anomaly detection, but it may capture noise instead of patterns if not regularized. So different inductive bias leads to different clustering, reduction, or pattern recognition outcome. Let's look at some good use cases for different unsupervised learning algorithms depending on their inductive bias. Customer segmentation for marketing is a good use case for k-means clustering, as it assumes customers naturally fall into distinct groups. And hierarchical grouping of genes in bioinformatics is a good use case for hierarchical clustering because it captures nested relationships between genes. Reducing high-dimensional text or image features is a good use case for PCA because it finds principal components capturing maximum variance. Market basket analysis, such as Amazon's recommendations, is a good use case for association rule mining because it identifies frequent items pairs like people who buy X also buy Y. And identifying flexible clusters in financial fraud detection is a good use case for Gaussian mixture models because they can model complex distribution in fraud detection. And learning complex representations for anomaly detection is good use case for autoencoders because they can identify unusual data points by reconstructing normal patterns. So the right model depends on the problem's underlying structure. So what if the inductive bias is wrong? Wrong choice leads to poor clustering, misleading dimensionality reduction, or false association. So that is a challenge. Another challenge is how to improve model performance. We can perform pre-processing that normalize or transform data to better fit assumptions. we can use hybrid models that combine multiple algorithms, such as PCA before k-means, for better clustering, and parameter tuning that adjust hyperparameters, such as choosing the right number of clusters in k-means or components in PCA. So model assumptions should match real-world data structures. Next, let's look at inductive bias for deep learning and artificial neural network. All right, so next let's look at deep learning. So deep learning models rely on specific architectural choice that introduce inductive biases, influence how they process data. These biases determine model strength and limitations, shaping their effectiveness in different tasks. So as we discussed before, inductive bias refers to the building assumptions that guide how a neural network learns patterns from data. These biases help focus learning on relevant features, improving efficiency and generalization. So it's important because it optimizes learning efficiency and prevents overfitting. And it also aligns architecture with data types. Some architecture work better for images, other for text or time series data. Choosing the right deep learning architecture means aligning its inductive bias with the problem. So for convolutional neural network, inductive bias assumes local connectivity and spatial hierarchies, focusing on nearby relationships. It excels in image, video tasks and detect edges, textures, and objects, but it struggles with long-range dependencies. Recurrent neural network assumes sequential dependencies, where the current state depends on previous inputs. They work well for time-dependent data like speech or text, but it suffers from vanishing gradient problems and limits long-term dependencies or long-term memory. And long short-time memory networks, LSTM, enhances RNN by capturing long-range dependencies and mitigating gradient issues. So it handles long sequences better than standard RNN. It's computationally more complex than simple RNNs. Transformers use self-attention to capture global dependencies without relying on position. It's superior for NLP tasks like machine translation, but it requires massive data and computing power. So different architectures work best for different type of data and tasks. For CM, a good use case is image classification, such as detecting cats versus dogs, because of spatial locality bias helps recognize objects effectively. For recurrent neural network on our long short-term memory, predicting stock market trends is a good use case because of sequential bias helps model time series dependencies. Also, speech-to-text transcription is good for LSTM because long-term memory bias captures spoken words effectively. And transformers is good for language translation, such as English to French, because of global dependency bias, which enables superior NLP performance. And CN, convolutional neural network plus transformers, is a good combination for autonomous driving perception because CN detects road features while transformers handle decision-making. So the right architecture depends on data structure and problem constraints. So a big challenge is choosing the right bias for the problem. What if an image model needs long-range relationships? So the solution is using transformers for vision, VITs, instead of convolutional neural network. What if an RN forgets long-term dependencies? So the solution is to use LSTM or transformers. Another challenge is computational complexity. Transformers outperforms RN in NLP, but they require more data and processing power. So convolutional neural networks are efficient for images, but may struggle with abstract reasoning. So we need to consider trade-off between accuracy, efficiency, and complexity. So inductive bias in deep learning architectures shape their strength and weakness. Convolutional neural networks excel in spatial data, recurrent neural network in sequential data, long short-term memory in long-term dependencies, and transformers in natural language processing. Choosing the right architecture depends on the problem, data types, and computational constraints. While inductive bias is essential for AI to learn and generalize, it can also lead to serious ethical concerns if not managed properly. AI models are only as fair as the data they are trained on. If the data reflects societal biases, the model will perpetuate and even amplify those biases. So key ethical concerns in AI inductive bias include reinforcement of existing biases, discrimination and inequality, lack of transparency and accountability, and potential to amplify stereotypes and exclude minority groups. So AI models can inherit biases from historical data and reinforce existing disparities. So in that case, AI can magnify discrimination instead of eliminating them. Inductive bias can result in unfair treatment of individuals and groups. For example, credit scoring model denied loans to minority communities based on historical data that reflects past financial discrimination. So that risk systematic exclusion from economic and social opportunities. So AI must be trained on diverse and fair data sets to avoid reproducing societal inequalities. Complex AI models, especially deep learning, function as black box, making decisions that even developers can't fully explain. So it can be difficult to challenge unfair decisions, and biases can go undetected, causing harm without accountability. So AI needs explainability tools to ensure transparency in decision-making. And AI models reflect and amplify gender, racial, and cultural stereotypes present in training data. Language models can associate nurse with female pronouns and CEO with male pronouns due to biased text in training data. Therefore, AI reinforces social biases instead of promoting equality. So bias detection and correction methods are essential to mitigate harmful stereotypes. AI models trained on non-representative data may perform poorly for certain demographics. For example, a voice assistant fails to understand accents or dialect from underrepresented groups. So AI can exclude marginalized communities and reduce access to service. So inclusive dataset improve AI performance for all users. Next, let's look at mitigation strategies for ethical AI. So diverse and representative data collection is important to ensure ethical AI. AI is only as unbiased as its training data. So we need to collect data from diverse demographics and ensure balanced representation of all groups. We also need to regularly audit datasets for bias. For example, facial recognition datasets should include a wide range of skin tones to prevent racial bias. Another technique is bias detection and correction. Bias is often hidden and unintentional. We must actively detect and correct it. We should use bias detection algorithm to audit AI model. And we need to apply fairness constraints to prevent discriminatory outcomes. And we should retrain model with debiased datasets. And transparency and explainability of AI systems is also important because users must understand AI decisions to trust and challenge them. So we can develop explainable AI models that provide insights into decision-making. We can use interpretable machine learning techniques like SHAP, LIME, and decision trees. And we should require documentation for AI models detailing their design, training data, and non-limitations. AI in healthcare, for example, should explain why it recommends a particular diagnosis instead of giving a black box answer. And ethical frameworks and guidelines are also important because AI must be built and deployed responsibly. We should establish AI ethics guidelines at organizational and government levels. We need to enforce regulatory policies to ensure fairness and encourage third-party audits of AI systems. In conclusion, AI inherits biases from data, leading to discrimination and unfair outcomes. Black box models reduce transparency, making accountability difficult. And AI can amplify stereotypes and reinforce societal prejudice. And bias detection, fairness audits, and explainability tools can mitigate these risks. Ethical AI requires inclusive datasets, regulatory frameworks, and ongoing oversight.